And welcome everybody to lesson number 4, which is solving logarithmic equations. So we're going to jump right into some examples. One thing to keep in mind is that we cannot have negative values evaluated inside of a log function. So if we get negatives along the line somewhere, can't happen. And that'll come up a little bit later in the lesson. But for our first example, right, log base 16 of x equals 3 over 2. We're going to change this into exponential form. Right, so keep my base of 16. This becomes my power. And this is what it's equal to. We have to remember some of our power rules here. Right, so this is going to be a square root. That's my denominator. Right away, I'm going to change this 16 to 4 squared. And that 3 is also going to be a power. I'm going to distribute the 3 to that 2. So we've got 4 to the power of 6 under the radical. That's going to come out as 4 to the third. And 4 to the third gives us 64. That value is positive, so that's our solution. So you have one right here for yourself to try. Pause the video and resume it when you're ready to check your work. Alright, let's check out how you did. We want to keep the same base, 27. We're going to raise it to the power of 5 to the 3. I'm sorry, 5 over 3. And it's going to be equal to x. This suggests cube root. And I'm going to break 27 up into 3 to the third. That 5 becomes a power on the inside of that radical. We'll distribute our 5. So we've got the cube root of 3 to the 15. And the cube root of 3 to the 15 is 3 to the 5th. 3 to the 5th we find to be 243. Calculator may have been needed for that. Okay, but that's as far as solving those simple logarithmic equations. For more complex ones, we have the property of equality for logs. And it tells us that we need to let b be positive and not equal to 1. And if we have the same log base, right, log base b of x, log base b of y, if they're equal, then that must mean that x is equal to y, right? We have the same base. That means what we're taking the log of would have to be equal. We can also go in the other direction with this. If we have two equal values, we can technically take the log of the same base of both sides. Okay, what that looks like here, right? We notice we have log base 8 of x and log base 8 of 20. That must mean then that x equals 20. Okay, that's how the property works. We're going to make it a little bit more interesting with some more sophisticated problems. Okay, what we got to be checking for, as I mentioned earlier, are extraneous solutions. Right, solutions or extraneous solutions are results that do not satisfy the original equation. What that means for us is that we're going to have to check our work because we can't have negatives inside of the log. Okay, now, does that mean that the solution you get can't be a negative number? It could be, but what happens is when we plug it back into the original equation, we can't have a negative inside of the log. So could we have a negative that works? Sure. Could we have a positive that doesn't? It's a possibility too. We're going to have to check no matter what. So let's take a look at a couple of problems that match this property of equality for logs. Okay. Here you notice the first problem, log base 5 of 5x minus 2 equal to log base 5 of 2x plus 7. We have the same log base. Because we have that, we can basically just eliminate it and work with the insides. Right? 5x minus 2 is equal to 2x plus 7. And now we can start solving. I'm going to subtract 2x from both sides. So 3x minus 2 equals 7. We'll add 2 to both sides. And then we'll divide. and we come up with x equals 3. Now, that's a positive number, true, but what the question is if we plug it in, first of all, is it equal? Do we get the same value out? And second of all, are both of those numbers positive? So we need to check. We want to make sure that this is equal. So is log base 5 of 5 to the 3 minus 2, is that equal to log base 5 of 2 times 3 plus 7? Well, 5 times 3 is 15 minus 2. That gives us 13. Here, 2 times 3 is 6 plus 7. That also gives us 13. So not only do we get the same number, but they're both positive, which means that x equals 3 works. Another example, log base 3 of x squared minus 15 equals log base 3 of negative 2x. We have the same base. So we're basically going to eliminate those and work with the insides. Now on this particular problem, I need to get all the x's on one side, and I'll be working with a quadratic, which means factoring. So let's add 2x to both sides. X squared plus 2x minus 15 equals 0. And now we can factor. I need two numbers that multiply to negative 15 and add to positive 2. So I'm thinking x plus 5 and x minus 3. We'll set each of those equal to 0. We'll get one solution as negative 5. And we'll get our second solution as 3. The question is, do either or both work? We gotta check. So here we go. We're gonna check for, oops, I spelled check wrong. We're gonna check negative 5 first. Even though it's a negative value, we want to make sure that it gives us a positive and that these two things are equal. So log base 3 of negative 5 squared minus 15. Is that equal to log base 3 of negative 2 times negative 5? Let's see, negative 5 squared is 25, minus 15, that's positive 10. So we got a positive inside. On the other side, negative 2 times negative 5 is positive 10. So we got two positive numbers that are equal, so this worked. Negative 5 was, in fact, the solution. When we check positive 3. Let's check positive 3. Is log base 3 of 3 squared minus 15 equal to log base 3 of negative 2 times 3. I'm already seeing a problem, right? Negative 2 times 3, that's going to give us negative 6. We can't have negatives. And when we check out the other side as well, right, 9 minus 15, that gives us negative 6 as well over here. It doesn't matter if they're equal, though, because we can't have a negative. So that means x equals 3 is an extraneous solution. Our only solution to this problem is negative 5. So there's a problem here for you to try out. It's going to involve extraneous solutions and most likely factoring. So pause this video and resume it when you are ready to check your solutions. Alright, I'm ready to check your solutions. Let's do it. I notice that we have the same base. So we can pretty much just get rid of those and work with the insides. We're going to move this 3x so it's on the same side as x squared. And that means we have to factor. I'm coming up with x minus 7 and x plus 4. And if we set each of those equal to 0 and solve, you would have come up with positive 7 and negative 4. But we need to check to see if either or both actually work. So here's our check. If we do 7 squared minus 28, is that equal to 3 times 7? Well, 7 squared is 49 minus 28. That's going to be 21. Well, at least it's positive. Let's see if they're equal. 3 times 7, that's 21. Both positive, both equal. That worked. X equals 7 is good. Let's check negative 4. Log base 2 of negative 4 squared minus 28 and log base 2 of 3 times negative 4. Uh-oh! So that's already a problem, right? Negative and positive. I can already see we've got a negative inside. I don't even really care what that happens to be. It's no good. It's not going to work. Our only solution here is x equals 7. Hopefully you got that same solution. We've got some other stuff to look at too. Not only are we working with equations, but we can also work with inequalities. Now here's the thing about inequalities. You have either you're going to get a range of values, and we need to figure out exactly what our range is. And depending on what we get when we first solve this, we'll either get an upper limit or we'll get a lower limit. If we end up with a lower limit right away, that's a good thing, because then we can just stop. We know that all solutions bigger than the lower limit will work, because they'll always come out to be positive. However, if we solve this right away and we get an upper limit, then that means we have to find the lower limit. And more than likely, we're going to get 2, and we're going to have to draw a number line to see which one fits all of our solutions into that range. Now that was probably really complicated listening to, so let's look at an example of how these work. Okay, and I will explain and show everything as we go along. Okay, so we have log base 9 of 12x plus 5 is less than log base 9 of 8x plus 9. The log bases are equal. Right, so right away we can get rid of those and just work with the stuff in the inside. But I'm going to keep this sign, right, less than. We'll solve just like usual, right? I'm going to subtract 8x from both sides. So let's see, 4x plus 5 is less than 9. Subtract 5. Divide by 4. And we get x is less than 1. Now that is what I'm talking about as far as an upper limit, right? It's telling us that x has to be less than 1. That means the max or the upper limit would be 1. So we have to now check for lower limits. Because if we plug in something too negative, it might not work. Right? But we can plug in some negatives. So here's the deal. We're going to take each of these things and we're going to set them greater than 0. Why? Because I know that these have to be positive when I plug a value in. So we want to figure out what the lowest numbers would be. So I'm going to take this first one, 12x plus 5. I'm going to make it greater than 0. I'm going to take the second one, 8x plus 9. And I'm going to make it greater than 0. And we're going to solve for both, right? Subtract 5. Divide by 12 here. So x is greater than negative 5 over 12. This one, we subtract 9. Divide by 8. And we get x has to be greater than negative 9 over 8. So let's see what's going on and which one we need to keep. For that, we need a number line. Here's 0. We know our upper limit is 1, so we're going to include everything from 1 down. But now we've got to figure out which one of these two we're going to actually use. And we're going to want the one that covers the overlap. And here's what I mean. Right, if we plot these two, right, negative 9 over 8, that's a little bit more than negative 1. Right, negative 9 over 8 is over here. And negative 5 over 12, it's a little bit less than half, right? It's here. And according to these, it says that they want everything greater. So if I choose here, and I choose here, I need the one that has the overlap, right? Here there's no overlap. So I can't necessarily choose values in here and satisfy this equation. But if I choose numbers here, it's going to work for both because it overlaps. So I don't want to use this one. That didn't work. This one did. So we're going to write our solution. I want my lower limit first. Negative 5 over 12 has to be less than x, and that has to be less than 1. That's our solution. Now I understand that was a lot, and I probably was blabbing a lot, but let's take a look at another example. We'll do this one together. Okay. Here we have log base 7 of 15x minus 6 is greater than log base 7 of 9x plus 30. We have the same log base. We can eliminate those. And we get 15x minus 6 is greater than 9x plus 30. Let's just keep on going. We'll solve just like usual. Okay, that gives us 6x minus 6 is greater than 30. We'll add 6 to both sides. I'm going to have to divide by 6. Now, here, we got x is greater than 6. That's a lower limit, right? That means that's the lowest x can be would be 6. We need numbers that are bigger than 6 from here on out. So does that mean that we have to search for an upper limit? Well, no. If we plug in any number here, it's always going to come out to be a positive number, because because we have to choose something bigger than 6, right? So if we chose like 7, that number is going to be positive. 15 times 7 minus 6. And it's going to work here as well, because I have a positive adding another positive. We don't have to check for an upper limit. And that's going to be the situation every time you find the upper limit. I'm sorry, the lower limit. All right, this is the lower limit. So if you find the lower limit first, you're good. If you find the upper limit first, you got to check for your lower. Okay, so you're going to have 2 practice problems of your own. I'll put them both on screen for you. And you can try them both out and resume when you're ready to check your solutions. All right, let's see how you did with these. Right away, we should notice that the same log base we can eliminate, and we're just going to work with the stuff on the inside, keeping the sign the way it was. And we want to start to solve just like usual. I'm going to add 26 to both sides and divide by 2. And we're going to come up with x has to be less than 9. Well, less than 9, that's an upper limit. That means we have to check for our lower limits. And we're going to have to take both of these pieces, set them equal to, or I'm sorry, greater than 0, and then draw a number line to figure out which one we want to keep. So 3x minus 8 greater than 0, and 5x minus 26 greater than 0. Let's do this first one. We'll add 8 and divide by 3. So we get 8 over 3 for our first limit. Our second one, we'll add 26 and divide by 5. We get 26 over 5. So now let's take a look at where these fall on the number line. All right, we know 9 is our upper limit. We want to include everything less than 9. But let's see what these ones look like. All right, 8 over 3, it's a little bit more than 2, right? That's 2 2/3. Here's 0. 26 over 5, that's a little bit more. That's like 5 1/5. And we're including values that are greater. The overlap occurs here at 26 over 5. So here's our range, and we're going to write it this way. 26 over 5 is less than x, which is less than 9. I'm hoping that you got that one correct. You needed a number line for that one. You had one more to do. Right, again, we had log base 3 on both sides, so we can eliminate the log base 3 altogether. So 9x minus 10 is less than 25 plus 2x. We'll solve just like usual. Let's see, add 10 to both sides. And we come up with x has to be less than 5. Oh, great. Less than 5. That's an upper limit. That means we got to check for the lower limits. Okay. So let's see. 9x minus 10 has to be greater than 0. And 25 plus 2x has to be greater than 0. Let's first start with this first one. Add 10 to both sides. Divide by 9. 10 over 9. So that's our first one. Second one, got to subtract 25 and divide by 2. And let's check it out on a number line. Negative 25 over 2, that's negative 12.5. Here's 0. 10 over 9, that's a little bit more than 1. And 5 is over here. So we want these numbers, and I can already see where it's going to overlap, right? Here's my first number. Here's my second. This is the overlap. So we want 10 over 9 less than x less than 5. All right, so those are logarithmic equations and inequalities. Not the most difficult thing in the world. However, the extraneous solutions and the upper and lower limits, those are the things that kind of get a little bit tricky. So if you have any questions on this, leave them in the comments, or better yet, bring them with you to class, and I'd love to answer them there. Can't wait to talk to you again.